For decades, one specific stretch of floating ice in West Antarctica has been quietly doing a job most people have never heard of, standing like a doorstop wedged against one of the largest, most unstable glaciers on the planet, holding it back from sliding into the ocean any faster than it already is. That doorstop is called the Thwaites Eastern Ice Shelf, and according to the scientists who have spent years watching it up close, it is now poised to break apart. Robert Larder, a marine geophysicist with the British Antarctic Survey who coordinates the UK side of the International Thwaites Glacier collaboration, put it about as plainly as a scientist can. The last bit of ice shelf in front of the glacier is poised to disintegrate. We don't know quite how this ice shelf is going to break up, he said, but it's definitely going to go. That warning is why Thwaites has earned the nickname most people actually recognize, the Doomsday Glacier, a label that first appeared in a magazine headline back in 2017 and sounded, to a lot of people at the time, like obvious exaggeration. It isn't. Today, we're going to walk through exactly what's happening beneath this glacier right now, why the structure holding it in place is failing, what happens once that last break finally gives way, and why researchers who have spent their entire careers being cautious about overstating climate risk are now using language this direct. If you've heard this glacier mentioned in passing without really understanding why scientists take it so seriously, this is the explanation that actually connects the dots. And if breakdowns like this help you separate real, well-documented risk from exaggerated headlines, subscribing genuinely helps this reach more people who need the accurate version. Let's start with the glacier itself, because its sheer scale is part of why scientists treat it so differently from ordinary glacial retreat, happening elsewhere on the planet. Thwaites Glacier sits in West Antarctica, and it is enormous, roughly the same size as the state of Florida, or if you're picturing this from outside the United States, roughly the size of Great Britain. It's the widest glacier on Earth. Since the 1980s, Thwaites has been losing ice at a steadily accelerating pace, shedding hundreds of billions of tons of ice and retreating roughly 12 miles, about 20 kilometers since 1992 alone. And in just the past 6 years, data shows the glacier's flow speed toward the ocean has increased by roughly 33%, an extraordinary acceleration for a body of ice this size to undergo in such a short window of time. To understand why that acceleration matters so much and why it's continuing to speed up rather than leveling off, you need to understand the actual mechanism driving the melt, because it's fundamentally different from the kind of straightforward surface-level melting most people picture when they think about a warming climate affecting ice. Thwaites isn't melting primarily because warm air is sitting on top of it, the way a chunk of ice left out on a summer day would melt from direct sun exposure. It's being attacked from below, at its weakest and most vulnerable point, where the ice meets the bedrock far under the surface. Warm, salty ocean water, water that's actually relatively warm by Antarctic standards even though it would still feel freezing to a human hand, pushes up from the deep ocean and works its way underneath the glacier, melting the ice from the bottom up at what's called the grounding line, the critical boundary where the glacier stops resting directly on solid rock and starts floating on the ocean instead. This bottom-up melting configuration is what makes Thwaites so dangerous compared to other kinds of ice loss, because it's structurally very difficult to stop once it gets going. As warm water melts ice at the grounding line, the glacier's base retreats further inland, and because West Antarctica's underlying bedrock actually slopes downward as you move inland rather than upward, that retreat exposes the glacier to progressively deeper water, and, in many cases, even more warm water contact, creating a feedback loop that can accelerate rather than stabilize over time. Researchers monitoring this process have found something genuinely alarming about just how far that warm water is actually penetrating. Using satellite and GPS data alongside underwater robotic exploration, scientists discovered that seawater is intruding more than 6 miles beneath the glacier itself, actively circulating and melting ice from underneath across a far larger area than earlier models had assumed, intensifying the melt in a way that wasn't fully appreciated until very recently. That underwater exploration work deserves its own explanation, because it represents some of the most difficult, physically extreme fieldwork happening anywhere in modern science, and it's directly responsible for a lot of what researchers now understand about this glacier's true condition. Since 2018, scientists working under the International Thwaites Glacier Collaboration, a joint effort between American and British research institutions, have deployed ice-breaking research ships and a specially built underwater robot named Icefin, engineered to swim directly into the narrow, dangerous cavity between the underside of the ice shelf and the ocean below it, an environment humans obviously cannot access directly. Icefin has captured direct video and sensor data from underneath Thwaites, documenting exactly how warm water moves, pools, and circulates in the cavity beneath the ice, information that would be essentially impossible to gather through satellite observation alone. That fieldwork has revealed a specific, troubling feedback mechanism. Cold meltwater draining out from underneath the ice shelf mixes with the warmer, saltier ocean water surrounding it. And researchers have found that this mixing process actually helps draw even more warm water in toward the glacier's base, rather than diluting or cooling it, reinforcing exactly the process driving further melt. And this isn't a slow, purely seasonal phenomenon either. Researchers tracking the movement of warm water eddies beneath the ice, swirling currents that can measure up to 6 miles across, found that meaningful changes in melting activity can be observed not just year to year, but within mere hours and days, a level of short-term variability that surprised even the scientists who had been studying this glacier for years. Now, let's talk about the ice shelf specifically, because this is the piece of the story generating the most urgent warnings right now, and it's the actual trigger behind the phrase "new warning" attached to this glacier. A floating ice shelf, like the one currently holding a good portion of Thwaites in check, functions as what glaciologists call a buttress, essentially a natural break pressing back against the immense weight of ice flowing down from the interior of the continent toward the sea. The Thwaites eastern ice shelf specifically sits at the glacier's mouth, partly anchored in place by an underwater ridge on the ocean floor that helps pin it against the outward flow of ice behind it. For years, that shelf has been slowly, steadily cracking. Researchers from the University of Manitoba analyzed 2 decades of satellite imagery from 2002 through 2022, tracking the growth of fractures clustered around what's called a shear zone, a region upstream of that critical pinning point where the ice experiences intense structural stress. What they found was a fracturing process unfolding in 2 distinct phases: long shear fractures gradually expanding over time, followed by a sudden spike in the number of smaller fractures branching off from them. Over that 20-year window, the total combined length of fractures across the shelf grew from roughly 100 miles to more than 200 miles. And in a detail that specifically alarmed researchers, even as the total fractured area kept growing, the average length of individual fractures actually decreased, a pattern that indicates entirely new stresses acting on the ice, essentially the shelf breaking apart into a greater number of smaller pieces rather than simply extending a handful of existing cracks further. By this year, that fracturing had progressed to the point where researchers are now describing the shelf's condition using language usually reserved for structures on the verge of imminent failure. Christian Wild, a geophysicist at the University of Innsbruck studying the most recent satellite imagery, described what he's seeing in blunt terms, saying that large areas of the shelf are simply falling to pieces. Major fissures are now clearly visible around the exact point where the floating shelf connects to the main body of the glacier behind it, and researchers monitoring the region have said the ice shelf is showing every sign of being poised to detach in the near term, with some estimates suggesting that breakup could begin as early as this year. It's worth being precise here about what that specific prediction does and doesn't mean, because it's easy for this kind of finding to get flattened into something more dramatic than what researchers are actually claiming. The eastern ice shelf breaking up does not mean the entire Thwaites Glacier collapses on the same timeline. The glacier itself sits primarily on land, grounded against bedrock, while the ice shelf is a floating extension attached to its seaward edge. Losing that floating shelf, on its own, wouldn't instantly or catastrophically raise sea levels, because floating ice, much like an ice cube already sitting in a glass of water, displaces roughly the same volume, whether it's frozen solid or fully melted. The real danger isn't the shelf breaking apart in isolation. It's what happens to the ice sitting behind it once that natural break is gone. And that's precisely the mechanism scientists are most concerned about right now. Once the eastern ice shelf loses structural integrity and eventually detaches, likely severing into multiple large fragments rather than breaking apart cleanly all at once, the restraining pressure it currently applies against the grounded ice behind it disappears. With that buttress gone, the interior ice sitting on land is expected to accelerate its flow toward the sea considerably faster than it currently is, and unlike the floating shelf itself, that land-based ice does directly raise global sea levels as it enters the ocean in exactly the same way that ice cubes added to a glass that wasn't already holding them raises the water level. Researchers have been careful to frame this properly. The loss of an ice shelf on its own is actually a normal part of how glacial systems behave over time. Ice breaking off into the ocean happens regularly around Antarctica without necessarily signaling catastrophe. What makes this particular event different is the specific role this specific shelf plays as one of the last remaining stabilizing features, holding back one of the most unstable, most consequential glaciers on the entire continent, and the fact that its loss is occurring within a broader pattern of accelerating retreat that's already been building for 4 decades. It's worth understanding exactly what's actually at stake if Thwaites eventually loses its grip entirely, because the scale of the numbers involved is genuinely difficult to process in the abstract. If Thwaites Glacier were to fully collapse on its own, current estimates suggest that alone could raise global sea levels by somewhere in the range of 65 centimeters to just over 2 feet. That's already an enormous figure, enough to fundamentally reshape coastal flooding risk for cities around the world. But Thwaites doesn't exist in isolation. It functions as something scientists specifically describe as a keystone or cork for the much larger West Antarctic ice sheet sitting behind it, a vast reservoir of additional ice that Thwaites, along with its neighboring Pine Island Glacier, currently helps hold in place. If Thwaites' retreat destabilizes that broader ice sheet and drags a significant portion of it into the ocean along with it, the resulting sea level rise estimates climb dramatically, with some projections suggesting a combined contribution in the range of 3.3 meters, and worst-case longer-term scenarios extending out over centuries, reaching as high as 11 feet, if the surrounding ice sheet destabilization continues unchecked. To put a number like 11 feet in perspective, that's not a scenario where isolated waterfront properties become vulnerable during storms. That's a scenario capable of permanently redrawing coastlines and displacing tens of millions of people living in low-lying coastal regions across the globe, from Miami and New York to London, Shanghai, Mumbai, and countless smaller coastal communities with far fewer resources available to adapt. It's important and genuinely reassuring in a limited sense to be clear about the actual timeline researchers are working with here, because responsible coverage of this story requires resisting the temptation to compress eventually catastrophic into imminent for everyone alive today. The International Thwaites Glacier Collaboration's own assessment, published after 7 years of dedicated field work between 2018 and 2025, states directly that although a full collapse of the glacier is considered unlikely to occur within the next few decades, the glacier is set to retreat further and faster through the remainder of the century and into the next, and that a broader collapse of the West Antarctic ice sheet over that longer multi-century timeframe simply cannot be ruled out. So far, despite all of this acceleration, Thwaites has directly contributed only a few millimeters to global sea level rise since large-scale measurement began in the late 1970s, a genuinely small figure relative to the scale of the warnings surrounding it. That gap between a currently modest direct contribution and a genuinely catastrophic long-term potential is exactly the tension driving so much scientific attention toward this specific glacier. It's not that Thwaites has already caused a disaster, it's that the structural signs currently visible, accelerating flow speed, an ice shelf actively fracturing and poised to detach, deepening warm water intrusion beneath the ice, are precisely the kind of signals researchers associate with a system approaching what climate scientists call a tipping point, a threshold that, once crossed, locks in centuries of continued, largely irreversible change, regardless of what happens with global emissions afterward. That concept of a tipping point is worth explaining carefully, because it's central to why researchers describe Thwaites' trajectory the way they do, rather than treating it like an ordinary gradual climate trend that responds proportionally to changing conditions. Once the grounding line of a glacier like Thwaites retreats past a certain critical point, particularly given that West Antarctica's bedrock slopes downward as you move further inland, the physics of the system can shift from a controlled, gradual retreat into a self-sustaining process that continues accelerating largely on its own, regardless of whether global temperatures stabilize or even modestly decline afterward. Researchers studying this dynamic describe it as fundamentally different from most other climate impacts people are familiar with, where reducing emissions today generally slows or partially reverses future damage on a corresponding timescale. A glacial system that has crossed its tipping threshold doesn't necessarily respond that way. It can continue collapsing over subsequent decades and centuries, even under a best-case future emissions scenario, simply because the physical process, once set in motion past a certain structural threshold, no longer depends primarily on the atmospheric conditions that originally triggered it. That's precisely why the specific structural signals researchers are watching right now, the fracturing pattern in the eastern ice shelf, the retreat rate at the grounding line, matter so disproportionately compared to a simple year-over-year temperature reading. They're trying to determine, in close to real time, whether this particular glacier has already crossed that threshold or is still approaching it, because the answer to that question determines whether meaningful intervention through emissions reduction can still meaningfully change Thwaites' trajectory, or whether its long-term fate is already effectively locked in regardless of what humanity does from here. There's also a broader oceanographic dimension to this story that connects Thwaites to changes happening across the entire southern ocean surrounding Antarctica, and it helps explain why the warm water reaching this particular glacier keeps intensifying rather than staying constant. Recent research examining compound drivers of Antarctic sea ice loss found that the ocean surrounding the continent has undergone what researchers describe as a fundamental structural shift, with heat that had previously remained trapped in deeper ocean layers now rising toward the surface, where it becomes available to melt both floating sea ice and, critically, the undersides of ice shelves like the one currently fracturing at Thwaites. That shift matters because it feeds directly into a self-reinforcing warming cycle. The enormous white ice sheets and sea ice surrounding Antarctica currently reflect roughly 80% of the solar radiation that hits them back out into space, while the comparatively dark, exposed ocean surface left behind as that ice retreats absorbs the vast majority of incoming solar energy instead. As sea ice coverage shrinks, less radiation gets reflected, more energy gets absorbed by the ocean, and that additional absorbed heat further warms the water, working its way toward glaciers like Thwaites, compounding the exact process driving the melt in the first place. This is precisely the kind of feedback loop that leads researchers to describe what's happening around Antarctica as occurring faster than existing climate models originally predicted, since a model built without fully accounting for this specific ocean heat redistribution mechanism will systematically underestimate how quickly a glacier like Thwaites can actually respond. It's worth pausing to put Thwaites' current condition in historical context, because understanding how quickly the scientific picture has changed helps explain why the urgency in researchers' language has escalated so noticeably over just the past few years. When the nickname Doomsday Glacier first appeared in a magazine article back in 2017, it was already grounded in real concern, but the level of direct close-range observational data available at the time was comparatively limited, based largely on satellite altimetry and broader regional modeling, rather than the kind of direct underwater grounding line level measurement that's become possible since. The formal launch of the International Thwaites Glacier collaboration in 2018 marked a genuine turning point in how thoroughly this specific glacier could actually be studied, bringing dedicated funding, specialized equipment, and repeated multi-year expeditions to a location that had previously been observed mostly from a distance. That shift from indirect, remote observation to direct, repeated, close-range fieldwork is precisely why the warnings coming out of this research program carry so much more specificity and confidence today than similar warnings did even 5 or 6 years ago. Researchers aren't simply extrapolating from broader Antarctic trends anymore. They're describing fracture patterns they've watched develop in real time across 2 decades of satellite imagery, and melt processes they've directly filmed happening beneath the ice using purpose-built robotic exploration. It's also worth explaining why Thwaites specifically, rather than any of the dozens of other glaciers ringing the Antarctic coastline, has become the singular focus of this level of dedicated international research investment. Part of the answer is straightforward physical exposure. Thwaites, along with its neighboring Pine Island Glacier, sits directly in the path of the Amundsen Sea's unusually warm deep ocean currents, making it one of the most physically vulnerable access points into the broader West Antarctic ice sheet, compared to other, more sheltered sections of the Antarctic coastline. But the other part of the answer is structural and geographic. Thwaites doesn't just represent a large glacier in isolation, it functions as one of the primary gateways controlling how much of the vastly larger ice reservoir sitting behind it, across the interior of West Antarctica, can eventually reach the ocean. Glaciologists sometimes describe Thwaites and Pine Island together as occupying a kind of geographic choke point, comparable in function, if not in scale, to a cork in a bottle. Their combined resistance is a major factor currently holding back a far larger volume of grounded ice from beginning its own accelerated retreat. That's precisely why researchers treat destabilization at Thwaites specifically as disproportionately significant compared to ice loss happening at glaciers elsewhere on the continent that don't play the same structural gatekeeping role. There's also a meaningful scientific debate worth understanding about exactly how catastrophic the worst-case collapse scenario for Thwaites and the broader West Antarctic ice sheet actually is, because the picture here has shifted somewhat, even over just the past couple of years, and it's worth presenting that shift honestly rather than only emphasizing the most alarming numbers. Earlier modeling work raised the possibility of what's called marine ice cliff instability, a scenario where, once an ice shelf's buttressing effect disappears, the newly exposed ice cliffs at the glacier's edge could become so tall and unsupported that they collapse under their own weight in a rapid cascading process, dramatically accelerating the pace of ice loss beyond what more conservative models predicted. That scenario is part of where some of the most extreme, multi-meter worst-case sea level projections associated with Thwaites originally came from. More recent simulation work, incorporating updated data on precisely how ice cliffs actually break apart under stress, has suggested that this particular cascading collapse mechanism may be somewhat less likely to unfold as rapidly or as catastrophically as those earlier worst-case models assumed. Importantly, researchers involved in that more recent, more moderate analysis have been careful to note that this finding doesn't mean the underlying concern about Thwaites has been resolved or meaningfully diminished. It simply narrows one specific, particularly extreme pathway among several plausible ways this glacier's retreat could unfold, while leaving the broader, slower, but still ultimately severe retreat process, the one driven by warm water intrusion, at the grounding line that we've spent most of this breakdown explaining, fully intact and, if anything, reinforced by the most recent direct observational data coming out of the eastern ice shelf's fracturing pattern. Let's also talk about what this means in very practical terms for the millions of people living in coastal regions who will experience whatever Thwaites ultimately does, not as an abstract scientific finding, but as rising water at their doorstep over the coming decades. Sea level rise, driven by a glacier this large, doesn't distribute itself evenly around the globe the way you might intuitively expect. Because a massive body of ice like Thwaites currently exerts its own small but measurable gravitational pull on the surrounding ocean, actually drawing water slightly toward itself, the loss of that ice mass as it melts and flows into the sea would, somewhat counterintuitively, produce disproportionately higher sea level rise in locations far away from Antarctica, including much of the eastern coastline of the United States, rather than concentrating the impact primarily near the source of the melting ice itself. That's a genuinely important and frequently overlooked detail in how this story gets communicated, because it means coastal communities in places like Florida, the mid-Atlantic states, and parts of Europe and Asia have a more direct stake in what happens to a remote Antarctic glacier than distance alone would suggest. Combined with the broader, independently documented weakening trend affecting Atlantic Ocean circulation patterns, itself partly influenced by freshwater input from melting polar ice, the practical planning implications reach considerably further than most people instinctively assume when they hear Antarctica mentioned in a climate headline. Because the scientific confidence behind these warnings didn't come cheaply or easily. Thwaites sits in one of the most physically inhospitable, difficult-to-access regions on the planet, requiring ice-capable research vessels, specialized cold-weather field camps, and purpose-built equipment like the Ice Fin robot, just to gather the most basic direct measurements. Researchers have described the field work involved as requiring drilling directly through hundreds of meters of ice to lower instruments down to the grounding line itself, recording temperature and current data in an environment where equipment failure or a shifting ice sheet can end an expedition or endanger researchers, with very little margin for error. The 7-year international Thwaites Glacier collaboration mission that concluded its primary fieldwork in 2025 represented one of the largest coordinated international polar research efforts of its kind, and the specificity of the warnings now being issued, down to identifying the exact fracture patterns, and the specific mechanism by which warm water is intruding beneath the ice, reflects years of accumulated hard-won direct observation, rather than distant modeling or speculation. It's worth acknowledging, too, how this specific research effort fits into the broader landscape of polar science funding and international cooperation, because sustained monitoring of a system this consequential doesn't happen automatically or cheaply, and the future of that monitoring is itself something worth understanding. The International Thwaites Glacier collaboration was structured as a joint effort between the US National Science Foundation and the UK's Natural Environment Research Council, representing one of the largest bilateral polar science investments either country has made in decades, specifically because of how disproportionately consequential this one glacier is relative to the broader West Antarctic ice sheet it helps hold in place. With the primary 7-year phase of that collaboration having concluded its intensive fieldwork in 2025, ongoing monitoring now depends heavily on continued satellite observation, supplemented by more limited targeted expeditions rather than the kind of sustained large-scale annual fieldwork that characterized the program's peak years. That transition matters for how quickly future warnings, like the one currently surrounding the eastern ice shelf's imminent breakup, can actually be identified, verified, and communicated to the public, since satellite-based monitoring, while continuous and valuable, generally can't replace the kind of granular, direct measurement that underwater robotic exploration and on-ice fieldwork provide, both scientifically and practically. Researchers monitoring Thwaites right now have described their approach in terms that convey just how closely the situation is being tracked, with scientists checking satellite imagery of the eastern ice shelf's fracture patterns essentially every single day, watching for the specific signs that would indicate the shelf's final disintegration is actively underway, rather than merely imminent. When that breakup does occur, whether within the next several months or somewhat further out, researchers expect it to unfold as a genuinely dramatic, visible event. Large sections of ice calving away and likely fragmenting into multiple enormous pieces, some potentially large enough to be tracked individually by satellite for months or years afterward as they drift and eventually break down further in the surrounding ocean. What happens in the months and years immediately following that breakup is really the critical open question driving ongoing research. Scientists will be watching grounding line retreat rates extremely closely, checking whether the newly unbuttressed ice behind the collapsed shelf accelerates at the pace current models predict, moderately faster than current trends, or dramatically faster in a way that would suggest the broader tipping point threshold has already been crossed. That answer won't be available immediately. It will likely take years of continued monitoring, using the same combination of satellite tracking, GPS instrumentation, and, when access allows, further direct fieldwork to determine which of those scenarios is actually playing out. So what does all of this actually mean for someone watching this story unfold from thousands of miles away with no direct connection to Antarctica at all? The honest answer is that Thwaites Glacier represents one of the clearest examples in modern climate science of a genuinely well-documented, well-understood physical process that nonetheless carries enormous uncertainty in its precise timeline, and both of those things are true simultaneously without contradicting each other. It's also worth resisting the urge to treat every individual update about this glacier, including the eastern ice shelf's current fracturing, as the final decisive chapter in the story. Researchers themselves have been explicit that climate risk of this kind tends to advance through a series of thresholds, rather than a single, smooth, easily digestible trendline. This year's specific headline about the ice shelf is unlikely to be the last major warning connected to Thwaites, and it almost certainly won't be the most consequential one either. It represents the loss of one more stabilizing feature, shifting the baseline conditions that future retreat will build on top of, which is precisely how large, slow-moving ice systems tend to move gradually from a chronic, background-level concern into an escalating, front-page hazard over time. The mechanism driving the melt, warm ocean water attacking the glacier's base is thoroughly documented through years of direct underwater observation. The structural failure currently underway in the eastern ice shelf is visible in satellite imagery and confirmed through detailed fracture analysis. The broader feedback loops accelerating the process, from ocean heat redistribution to declining sea ice reflectivity, are increasingly well understood by researchers studying the Southern Ocean as a whole. What remains, genuinely uncertain, is the precise pace at which all of this will translate into measurable global sea level rise over the coming decades and centuries. Whether Thwaites' retreat stays on something closer to the currently modeled multi-century trajectory, or whether the accelerating signals researchers are documenting right now indicate the glacier has already crossed into faster, more self-sustaining territory than existing models have fully captured. So here's the real question worth sitting with as this story continues developing, likely within the coming months, given how closely researchers are watching that fracturing shelf right now. If a structure that's been quietly holding back one of the largest glaciers on Earth is genuinely poised to fail, and the scientists studying it up close are using words like definitely going to go, rather than their usual careful hedging, how much longer should coastal communities around the world be treating this as a distant, end-of-century abstraction rather than a live, actively unfolding process worth planning around today? Let me know in the comments whether this is the first time you've actually understood the real mechanism behind why this specific glacier gets so much attention, because a lot of people have heard the nickname Doomsday Glacier without ever hearing the actual science explaining why it earned it. If this breakdown gave you a clearer, more grounded picture of what's genuinely happening beneath the ice right now, share it with someone who'd find the full context useful, and subscribe for more deep dives that explain the real research behind headlines like this one, because the researchers watching Thwaites are checking that satellite imagery again tomorrow, and the story is very much still being written, one fracture, one grounding line measurement, and one carefully worded warning at a time.